Hello to everyone that's just joined us there. We're just waiting for a minute or two for people to join the webinar. We'll get cracking then. So if anyone has just joined us there, we're just waiting a minute or two for people to join up, and then we'll get going in a second. All right. Okay, so let's get going. You're very welcome to the IRI Technical Seminar Series 2024. We're on the subject of pump energy consumption and control. So optimizing pump performance in ice water and glycol-based cooling systems. So really what we're talking about here is centrifugal pumps, which would be used for the most part in ice water and glycol-based cooling systems. And we're just going to have a little kind of chat about some of the theory behind it, and then look at some examples. And then I'm going to talk a little bit about some of the work that I've done in my own business here, Kilkenny Cooling, just some of the research work that I've done and the results that I've gotten from working to optimize cooling pump performance. So talking about performance. So when we're talking about a performance for any system, it can be anything at all. It can be a pump, it can be an engine, a mechanism, anything really. What we're seeking to do is kind of understand the input and output and the relationship that exists between those two things. And if we can kind of get a handle on that relationship, try to understand it, maybe understand the maths behind it a little bit, maybe graph it, it goes a long way towards being able to optimize that performance. So as I say, it can be any kind of a system at all, really. An input could be something like time, fuel, power, energy, anything. And again, your outputs could be anything at all, you know, heat, speed, power. So, I mean, if you took something like an engine, you could be putting in fuel and measuring your power output and trying to understand that relationship. So really what we're trying to do here today is understand these input-output relationships. And there are a set of simple relationships that govern how centrifugal pumps behave. And if we can work to kind of understand those a little bit better, it will allow us to optimize them a little bit more. So what I'm going to do is just talk about some very, very simple real-world non-pump related examples of these kind of input-output relationships. And the reason for that is to try to introduce this concept of being able to understand them, maybe graph them mathematically. So if you take a very, very simple relationship, a baking relationship, okay, where you're making cakes and you know that it takes 2 eggs to make a cake. We know that if we have 4 eggs, we can make 2 cakes. And if we have 6 eggs, we can make 3 cakes. And all the way forward on 20 eggs, 10 cakes, and all the rest of it. We call that a linear relationship. And look, it's a very simple thing. It's not something that we really think about mathematically or that you'd ever graph. But what it means is that understanding this input-output relationship allows us to make predictions about how that system or how that's going to behave. So we know if someone comes along and says they've got 1,000 eggs, we know how many cakes we can make out of that. And I don't think anybody's ever going to graph that, but you actually can graph it if you like. And it's a linear relationship. And one of the relationships, the input-output relationships when it comes to pumps, is also a linear relationship. And we're going to talk about that very shortly. But this is just a very, very simple example of how you can model an input-output relationship for a system. So the follow-on question from that is, are there other linear relationships in the world around us that we can use as examples to maybe try and further understanding of how that works. So time, speed, and distance is a really, really good example of a linear relationship. So if you're traveling at a set speed and you decide that your destination is twice as far away, you know it's going to take you twice as long to get there. It's a directly proportional relationship. And likewise, if you're going a set distance and you double your speed, so you increase your speed by a factor of 2, you will reduce your time by a factor of 2. So you'll half your time. Linear relationship. Another example of that, again, a simple one from day-to-day life. If it takes a tin of paint, if you can paint 10 square meters of a wall with a tin of paint, you know, if you have 2 tins of paint, you can do 20 square meters, 3 tins of paint, and on and on and on. Plot that on a graph, you'll get a straight line, linear relationship. Very, very simple. Water depth and pressure, also a linear relationship. And there's a direct proportion between how deep you go on the pressure that you will experience at that depth. But the question is, these are simple day-to-day linear relationships that exist all around us. Are all input-output relationships linear? So if we're putting something into a system, whatever that system might be it a machine, a mechanism, a pump, is the output from that, can it be predicted in a linear fashion in the same way that all these can? And the answer, of course, to that is no. There are more complicated relationships, and I'm going to give you another, again, non-pump related, but a very simple kind of real-world example of how this might be easy to understand. And you know, the reason I'm doing this is because sometimes people find the idea of a non-linear relationship, a relationship of maybe a diminishing return, kind of slightly hard to wrap their head around. So if we take a very simple, different example of a farmer with a field, and let's just say he puts 10 kilos of fertilizer on his field and he gets his crops out at the end of the year. The question we're asking is, if he doubles his fertilizer input, will he get double the amount of crops out at the end of the year? If he triples his fertilizer input, will he triple his crop output at the end of the year? And can you just keep adding fertilizer and keep getting more and more crops? And can you plot that on a straight line? I think we all know the answer to that. Again, nobody gets too mathematical about these things. It's nearly kind of intuition or gut instinct that you know, and that the farmer knows that there's a sweet spot for fertilizer there where he'll get the crops he wants. And after that, he can add more fertilizer. Maybe he'll get some more, but he's not getting value for money out of it. And eventually he's going to keep adding fertilizer, and he's going to get no extra crops out of it at all, and he's just wasting his money. And I suppose the ultimate outcome of that would be he would just kill the crops with too much fertilizer. So if you actually graph that, it would probably look something like this. So what he's aiming to do, what the farmer's aiming to do, is optimize it there, find that sweet spot for fertilizer per crop output, and in his nonlinear relationship. So are there other nonlinear relationships all around us? There are some with the pumps, and we're going to talk about those in a minute. But again, in day-to-day life, there are lots of them around us. Fuel consumption and speed is a good one. So, you know, if you are traveling at a certain speed and you decide to increase your speed by, let's say, 10%, your fuel consumption might go up by more than 10%. You get a diminishing return. And it's very, very interesting to look at scenarios with you know, maybe motorsport or aviation and things like that, where they're trying to push this to its limit and see the amount of input they would have to put into a system like that to get that extra little bit of speed out. So that's a nonlinear relationship. Staff levels and work done can also be a nonlinear relationship. Simple example, if it takes one person a day to put in an air conditioning unit and you put 10 people on that one job, are they going to get it done in 1/10 of the time? I think the answer to that we could safely say is no. There's a sweet spot there of maybe 2 people or 3, and after that you can keep adding people and it's just not going to make any difference. Pump speed and pressure is a non-linear relationship, and we're going to look at that in a little bit more detail shortly. But what it means is that it's not directly proportional. It doesn't form a straight line on a graph in the same way the other linear relationships did. And again, pump speed and power consumption, non-linear relationship, and we're going to talk about how this works in a little minute or two. So really, these linear, non-linear relationships are what it all boils down to are the pump affinity laws, and these are a set of laws which govern how these centrifugal pumps behave. And understanding the relationships and understanding these laws, you don't even have to get very, very mathematical about it. I think a general familiarity with the way that these work is very, very beneficial when it comes to optimizing pump performance. So the first, we're just to recap, the pump affinity laws are the mathematical relationships between the several variables involved in pump performance. So variables, we're talking about pressure, we're talking about RPM, the pump speed, we're talking about the flow out of the pump, the power consumption of the pump. These are all variables in that system, and the pump affinity laws describe the mathematical relationships that exist between them. So the first affinity law says that the flow capacity, the flow out of the pump, varies directly with impeller diameter and speed. Now, we talked, our very first example of the cake and the eggs was a linear relationship. So straight line on a graph, you increase one by 10%, the other increases by 10%. It's a directly proportional relationship. So the first affinity law says that flow capacity varies directly with impeller diameter and speed. The second affinity law is a nonlinear relationship. It's what we call a quadratic relationship because of the square here. So what it means is that the pressure that the pump delivers varies directly with the square of the impeller diameter and speed. So it's nonlinear. If you plot this on a graph, you will get a curve, a quadratic curve. And the final affinity law, which is possibly the one we're most interested in for the purposes of this conversation, the power consumption of a pump varies directly with the cube of the impeller diameter and speed. Again, nonlinear. This is a more, if you like, in layman's terms, more extreme version of this. What it means is that speed variations will have disproportionate effects on power consumption, and speed variations here will have disproportionate effects on the pressure, and it's more pronounced. That disproportionate effect is more pronounced here. Now, a pump is generally something that's going to be off the shelf. You're going to have it. It's not something that you're going to be able to vary the diameter of the impeller. Now, just to talk about the impeller, that's a little vane. It's a round thing like a windmill, which rotates in the pump, which is what allows it to pump the water or the coolant. But the laws tell us that things change if we vary the impeller diameter, but we're actually realistically in the real world not going to be varying that impeller diameter because it tends to be a fixed thing that's part of the pump. So what that does is it removes it as a variable in our mathematical equations, and it makes it a constant, which simplifies everything. And it allows us to simplify the affinity laws right down to three basic statements. Flow is proportional to speed. So the RPM of the pump is directly proportional to the flow out of the pump. The pressure of the pump is proportional to the speed squared, nonlinear relationship, and the power consumption, that's in green because we're quite interested in that, and that's proportional to the speed cubed. So what that means in the real world is that small changes in the speed have a much more drastic effect on the pump's power consumption. So if we just look at how that's graphed, there's our affinity law number one, directly proportional relationship, linear, straight line. So if our input into this system is our speed, and our output, where the relationship we're interested in is our flow. So we know if we reduce our speed from 100% of the design speed of the pump down to 70%, our flow rate is going to correspondingly reduce from 100% to 70%. It is a directly proportional relationship, straight line on the graph. As I said, affinity law number two, it's a nonlinear relationship, it's quadratic. So what that means is that speed changes have a more significant effect on the response. So here we see that a speed reduction from 100% to 70 has an effect of reducing the pressure from 100% to 49. So it's a more significant reduction. And that's due to this curve, a quadratic curve. And the final affinity law is the power consumption law. And that is a cubic curve. So you can see the curve is more pronounced there. And what that means is that if we reduce our speed from, say, this is just an example, it can be anything, but we say 100% to 70%, our power consumption is going to reduce from 100% to 34%. So that is a very significant reduction in power consumption. So in the refrigeration industry, what are we interested in? We're interested in pressure and flow rate requirements for plate heat exchangers, jacketed vessels, dry coolers, beer line pythons, and many more. Flow rate in particular is one that we're quite interested in, in terms of the likes of a heat exchanger. if you're buying a heat exchanger or specifying one for a process, one of the key parameters that you're going to have to provide to whoever's giving you that heat exchanger is the flow rate of the coolant through it. So it is a very important thing to be able to regulate when it comes to refrigeration. Same with jacketed vessels. The faster or the more volume of coolant that you can pump through the system, the faster your cooling process is going to be, or the more effective your cooling process is going to be. I have beer line pythons highlighted there in bold because I've just happened to have done a lot of work on that, and I'm going to share some of the results of what I've done with you, and we can actually see how this works in terms of the real world and getting actual data back from making some of these changes. So we can see that the speed with our affinity laws has a huge bearing on things like pressure, flow rate, and power consumption. But the thing is that an awful lot of pumps are fixed speed pumps. They're a single phase motor and they operate at a fixed speed. So if you think of any standard centrifugal pump that you will come across, you go down to your little special buys on a Thursday morning and you buy a pond pump, it's going to be a fixed speed pump probably. And you can actually work out the RPM of that pump. It is 120 times the supply frequency, which in Ireland will be 50 hertz, divided by the number of pole pairs. So the frequency and the number of poles is what determines the RPM of the motor when you plug it in. And these tend to be fairly standard off-the-shelf items. So a pump designer is going to optimize that pump's hydraulic assembly for that speed. So they're going to have a motor and they will have a set of pressure and flow rate requirements given to them by their customer, whoever is buying the pump or whoever needs to use it. So they'll have these affinity law requirements, and someone will come to them and say, look, I need 100 litres a minute, I need 3 bar of pressure, and here's your pump turning at 2800 RPM, say. I want you to design the impeller housing and I want you to design the pump to optimize for these specific set of requirements. So when that designer optimizes for those requirements, that's great because that's optimized for those requirements. But the question is, what happens if not all applications are the same? And this is something that I come across all the time, where we have an optimized single phase pump off the shelf and a variety of actual applications that are quite different from one another. And the question we need to ask is what happens in terms of power consumption and performance if the applications are not the same. So this is a beer cooler. Again, this is a project that I tend to do a lot of work on, so I'm using it as an example. For those of you who are not familiar with how a beer cooler works, it's basically an insulated tank of ice water, and it circulates ice water up to the bar. These lines have beer in them, but there's also ice water circulating to that bar. And in Ireland, you'd probably have, if this was in a hotel, you might have a bar, you might have a function room, you might have a lounge area. So you'd have you'd have a distribution manifold where this water feed from your single pump is split into 3, and it circulates in this insulated line up to the bar and back down. So the water pump is a key component in this product for us. So we see scenarios all the time. I see them where I have a standard pump, a standard application, or a standard pump, and the applications vary very, very significantly. So what happens in that scenario? So I'm going to actually give you an example, and I've taken these measurements and I've done the work on this, so I can tell you in real world terms what actually does happen. We take a standard beer cooler and we're pumping water to 3 places. We're pumping it to the main bar 30 meters away, to the lounge 25 meters away, to the function room 25 meters away. And we take that exact same beer cooler and we put it into a different place. Let's say pub A is a hotel, busy hotel in the city centre or whatever. It's got these 3 rooms in it. Outlet B is a small country pub. It's got a lounge and a bar, and they're both 10 meters away, or 10 meters away and 8 meters away. Much lower resistance in the water circuits here, and everything else is identical. And the question we ask is, do they use the same power? And I give this example to, kind of people in the industry who occasionally will call into the factory to discuss this sort of stuff. And I get a variety of answers. Some people think, well, they're the same machines, they use the same power. Some people will say machine A will use more power because it's got much higher resistance, it has to pump much further. There's more water in the circuit, it's going further. This is going to use more power to pump the water. And then other people will say that it's B. So I get a mix of responses from this, and I can tell you that the answer is B. B uses probably about 20% more power in that, and that's, you know, for people who work in the industry or working with pumps, they understand this, but it's kind of counterintuitive for people who may not be that familiar with it. They would say, well, there's much more resistance here. Why is this not using more power? But if you go back to your affinity laws, you will see that when the flow rate increases, the impeller speed will slightly increase. A slight speed of impeller speed will result in a significant power input requirement. So that's the reason for it. So lowering your actual resistance here is going to result in more power consumption. So clearly speed control is the answer here. Now, if you don't have speed control, you can actually just put resistance into this line in the form of valves, and that will reduce your power consumption. The optimum scenario is speed control. So let's just look at our affinity laws again. Flow rate is directly proportional to pump speed, as we discussed. Affinity law number 1 is a linear relationship. So if reducing the flow rate by 30% in your system, and it doesn't have to be a beer cooler, as I say, this can be a jacketed vessel, it can be a plate heat exchanger, anything at all. If reducing your flow rate by 30% is feasible, then the speed of the pump, the RPM of the pump, can likewise be reduced by 30%. So you say, look, okay, here's the system. The pump is doing 100 litres a minute, but we really only need 70. We can reduce our flow rate. That results in a speed reduction of 30%. But because of this non-linear relationship here between the pump speed and its power consumption, if we reduce that speed by 30%, we have a massive, massive drop in power consumption. So power consumption can be reduced by, in the case of a fixed speed pump, as I said, reducing the flow rate with valves and restrictors in the line. But the ideal scenario is you use a variable speed pump and you set the speed of the pump with a variable speed drive. This is an ABB drive that I've just happened to use, but they're, you know, I'm not promoting one brand over the other. We have to be very careful about that. But this is a simple just speed control drive. And what we discussed earlier was that the speed of a pump is a function of its supply frequency. So if you have a single phase plug-in pump, that's going to operate with a 50 hertz supply frequency. But what this device does, the variable frequency drive, is it actually will take the line frequency and it will provide the pump with a different frequency. You can set it to a different frequency, so you can actually slow it down. That's the way that works. Just a quick recap again, reducing that speed with this cubic affinity law, this is our power speed relationship. Reducing that speed gives you a massive drop in power consumption. So optimizing power consumption. So really what we're talking about doing is using a variable speed drive insofar as it's practical. So how would you actually go about doing that? And if you think about a scenario with a reasonably constant cooling demand, and I'm just thinking from personal experience, a good example from my own work that I've done would be the providing cooling systems for bakeries, because in a scenario with a bakery, they would generally have the same demand every day. They would use the same amount of water. The water is coming in pretty much at the same temperature, or, you know, week to week, might vary over the year. And it's very predictable. So what you would do there is you would figure out your minimum flow rate to give you the results that you're looking for. Select an appropriately sized pump. And I've seen this time and time again, that like guys will just say, oh, you know, what do I need? 50 litres a minute. Oh, this one does 100 litres. Oh yeah, sure, it's grand, because you know, I mean, it'll get the cooling job done and everything is happy. Everyone is happy because you don't have any technical issues. But as we can see from the affinity laws, that if you're pumping more water than you need to, you're going to use way more electricity than you need to. So you will select an appropriately sized pump, or close enough to it. Maybe it's a little bit oversized, and then you can reduce your flow rate with valves and restrictors if required. That's for a single phase pump, but the ideal scenario is that pump can be speed controlled. So you would set the speed of the pump at a variable speed drive. So if you had something like a bakery, you would set that speed to just give them the temperature that they're looking for. Anything that any greater pumping than that is just wasting electricity, essentially. And then, you know, if you have a scenario where the bakery's production increases, or summertime, the water coming into the heat exchanger is a little bit warmer, you can speed that pump up. And again, you're using the exact amount of power that you need to. If you have a scenario with a significantly varying cooling demand, and this is something, again, I see in work where I would get a project where I would have someone that might be making soup in a big kettle. So that's one we've done a good few times. And when that soup comes out of the cooking process, it needs to be cooled very, very fast. And so you need to use a lot of water to do that initially, get that temperature down. But once it gets to, say, 4 degrees or whatever the temperature is, they mightn't actually need it straight away for packaging. They might just need to keep it there. So maintenance cooling using all that water is just wasting electricity. So really what you want to do is you want to regulate the amount of coolant going through that down for maintenance cooling. So the idea here would be that you would control your variable speed drive. So what you do is you take a temperature, you sample your product temperature wherever it might be it at the output of the heat exchanger, or maybe the temperature probe inside in your vessel where you're cooking the food or whatever, and you regulate your pump speed accordingly. Again, I'm not recommending one brand over another. This is a Carel IR33, which is a model I've used myself for this application. So what this does is it will take your temperature and it will give a 1 to 10 volt control signal, and that control signal will talk to your inverter. So here's a scenario where you have a plate heat exchanger, you have a product going through it. You sample your product output temperature, and you can regulate the speed of the coolant going in automatically using a drive and a controller. And they're very, very customizable. You can use them for, say, lots of different applications. And essentially what that's doing is it's providing the precise amount of cooling that you need and no more. Now, I've very, very little experience in kind of HVAC and aircon and that kind of thing. It's not my area of work, but I know that these kind of variable speed drives and this kind of an approach is much more common in that space. But I think that when we're talking about inverter drives and condensing units and that, it's becoming more and more common. This technology is becoming a lot cheaper, more readily available as well. So really everyone should be looking at doing it. Now here's something different. This is my test rig, which I have in the factory here. I use it for a few different things. I use it for simulating various site conditions. So what I will do is I will go to a site and I will measure flow rates in bare line pythons in a pub, and then I can record them and I can come back and I can set that up on this system using a variety of pumps. So I can simulate what the pub is doing, and then I can regulate the flow using these inverter drives and our sample pumps, and measure using this energy meter the output from that. So I use it as more of a demonstration piece. I've used it for a lot of R&D in the past, but nowadays I have it set up and I use it as a demonstration piece where people can actually really see the results from regulating the flow rates in the pythons. But again, you can set this up for anything. It wouldn't just have to be a bar application. Now, I'm going to share with you some of the actual findings from setting this up. So what I did was I went to a site and measured the bare cooler flow rates, and then I set that up on the system with our standard fixed speed pump, and then I use it with our new electronic drive pump. So this is an EC motor, very common in fan motors, but now we're seeing them more and more in pumping motors, and they're getting smaller as well, becoming much more affordable. So I think we're going to start seeing more and more of these in the industry. These are the results. So this is a simulation in the factory, one of the factory trials that I did, where I measured 2 pythons delivering 13 liters per minute in each. So our fixed speed pump is running at 2800 RPM and it's drawing 500 watts. But we don't actually need 500 watts for that cooling process. The specification that's delivering 13 liters a minute in each python. But we don't actually need 13 liters a minute in each python for that process. The specification is 6. So what we can do is we can replace it with a more modern pump, and we can speed control it. And if you just look at the saving here, went from 500 watts down to 100 watts, delivering close to our specification there. So the conventional pump is using 5 times more power than our EC prototype pump. And you know, I think there's no arguing with that saving. So having done some of these trials in the factory, what I did was I actually installed some on sites. That was in the factory. What about the real world is the question, and the savings are real. So I'll just give you some examples I did. I went to a site in a GA club. It's a bar with two 25-meter pythons up to each bar with a conventional pump. So I replaced the fixed speed water pump with the speed controlled electronically commutated pump, and our pump power consumption went from 13.2 down to 2.6 kilowatt hours per day. So that was a massive, massive reduction. And the actual condensing unit power consumption reduced as well, which is kind of a side effect from by virtue of the fact that the EC pumps are much more energy efficient. They don't give off as much heat. It actually reduces your refrigeration consumption as well as a side effect. So the overall running costs in that place reduced by 70% in their draft beer system, which they're very, very happy about. They're saving over 1,600 a year. Now, look, in an industry application, with if you have a big, massive bakery, a big factory, they mightn't be getting too excited about 1,600 a year. But if they have multiple machines, or if you're, like in this example, you are putting it into a place, like it's a small place, and their cooler consumption is a significant proportion of their consumption for the year, then yeah, they are. That's a significant saving for them. Identical beer cooler in a different pub, we did a before and after study on 68% power reduction and energy savings of 1,580 per year. And that testing was independently supervised as well by the Southeast Technological University and Diageo. So we can stand over the figures. Now, in these applications, these were brand new coolers before and after, but in this one, I took a pub that was replacing an old beer cooler and measured the pumping, measured the power consumption before and after. And we got a running cost reduction of 84%. 84%. The guy said that his actual power consumption for the entire pub halved, so he's very happy, saving $2.5 grand a year. So that concludes the presentation. My email address is there, and my LinkedIn as well. If anyone has any queries or questions or anything, if anyone is interested in coming down to the factory and having a look at that test rig that I have set up, you're more than welcome to come down, have a play with it, have a look at how the different pumps perform and operate and everything, or you're welcome to just drop in. I think there's a facility. I'm kind of new to Teams, so I think there's a facility on this to ask a question. I don't know, Karen, if you're there, maybe you could advise as well. Or otherwise, you can just drop me an email or drop me a message on LinkedIn or Connect or all the rest of it, and I'll happily share it with you.
Yeah, John, I think there's a Q&A section up the top there. Yeah. So if anybody has any questions, you can pop them in there, and you can have a look, or in the chat, whatever's easier.
Yeah, or drop us an email either. I hope that was useful and for people. It's very hard to know how exactly what way to present a kind of a technical question, so or technical seminar. So let me see. I don't have any Q&A. I must have. Oh, Robin Allen says thank you very much. Thank you very much for that. Yeah. So nobody else. I must have covered everything. So is that all right, Karen? Are we good to leave it there unless?
There's another comment there.
Oh, in the chat. Sorry.
Yeah.
You'll have to forgive my newness to. Michael says thank you. Thank you very much, Michael, for attending. Yeah. That's great, folks. Give it another minute in case somebody is furiously typing a question. Hopefully I'll be able to answer it.
There's a question in there. What is the future for pumps? Thanks, Declan.
A very open-ended kind of question. I wish I knew the answer. But just from my own, all I can talk about is my own experience and just looking at these things. I can see the cost of a lot of the control and the technology is coming down. And I think people are more, as well as the cost coming down, what's happened is energy prices are going up. So it's making things that, you know, maybe were not worth buying now more viable. So like that EC electronic pump with the control system I was talking about there earlier, that, you know, 5 or 6 years ago would not have been viable because electricity was too cheap to make it save enough money. And also, I think the technology at the time was probably too expensive. So I think we're going to probably see things getting cheaper. And I think we're going to see much more people adapting this kind of thing, because speed control, because the potential for savings there are too great to be ignored. You know, the payback on these is, you know, less than 2 years. In some cases, it's less than a year. So that's how I would see it as well. Definitely EC motors, they're brilliant. They're the electronic motors with the permanent magnets in them. They would typically have efficiencies of over 90%, whereas your standard single phase induction motor might be something like 60 to 70%, and the rest of that is just dissipated in heat and noise. And in refrigeration scenarios, we don't want stuff dissipated in heat, because then we have to remove the heat, and that's more refrigeration. And I saw that with the beer cooling work that I did. Putting heat into that, it's just, you just have to get rid of it somewhere, and that costs more money. So I hope that answered your question, Declan. Okay. We have no more comments or questions. Folks, thank you all very much. I do hope that was you. Oh wait, there's someone typing a question. Me all again. And then we'll go off for our spuds. Have I found gains in insulating the pipes? Okay, so a lot of the work I've done has been before and after studies on well-insulated pipes. And the reason for that is because I needed to show that the system itself was better, rather than it's better by virtue of the fact that we're now using insulated pipes. So when I'm working with the beer coolers, if I'm going to, say, a brewery, and I replace some old system that's been in 20 years, and they get fantastic energy savings. And you can see an example. I had an example of that. You get brilliant energy savings, but some of that is down to the fact that a lot of the old pipework, the pythons, are being replaced because they're old, and the new stuff is much, much better. So those gains of kind of 60, 70% that I saw in the work that I did is before and after using the exact same pipework. So there's no gain there from insulating pipes. But definitely, I know from a beer cooling point of view, insulating python has a huge impact. And it actually also has an impact on the beer as well, beer quality and the beer temperature. So that there is definitely a, unfortunately, I don't have any figures for you on that, because my work has generally been more on the motor and the pump side, but there is certainly a benefit to pipe insulation. That's my own take on that. Thank you very much. Okay, will we wrap it up there, Karen? And look, there's my details if anyone wants to drop us an email or anything else. And as I say, you're all more than welcome. Just give me a little bit of notice and you can call into the factory and have a look at what I'm doing here, if it's something that's of interest to you personally. All right.
Okay, thanks, John.
All right. Thanks a lot, Karen. Thanks everyone.
Bye.
Bye now.